Grand Canyon is 1 mile deep, 277 river miles long, 17 miles wide in some stretches. Now, those numbers get repeated so often they stop meaning anything, but here is the number nobody leads with: 4,300. That is the number of places inside Grand Canyon National Park where archaeologists have formally documented evidence of prehistoric human activity. Not campsites, not passing through, roasting pits, quarries, storage structures, mines. 4,300 recorded extraction sites inside a single national park. The National Park Service confirmed this figure through their ongoing survey, which included 136 days of active excavation between 2007 and 2009, the first major dig in the canyon in nearly 40 years. The project recovered stone tools, pottery, jewelry, fire hearths, and, this part matters, quarry marks, evidence of people removing material from the earth on a massive and sustained scale. So, before we go anywhere else, let us answer the first question straight. Yes, the canyons were mined. Not occasionally, not by one culture. For thousands of years by multiple distinct civilizations, using techniques sophisticated enough to extract specific minerals from specific geological layers across a landscape the size of a continent. The oldest sites in the Grand Canyon River corridor date to the Archaic period, roughly 9,000 years ago. 9,000 years of documented human presence in a place tourists stand at the rim of and describe as untouched wilderness. The second question is the one this video is about. When you remove billions of pounds of material from a landscape across centuries, and you dump the waste rock in piles near the extraction sites, and you burn thousands of acres of surrounding forest to power the smelters, and you do this repeatedly at dozens of sites across multiple geological regions, what does that landscape look like 2,000 years later? Dry, scraped, red-brown, flat in stretches, broken in others, mineral-crusted, bare, what we call desert. If documented history told from primary sources is why you are here, subscribe. It is the best way to support this research. And drop a comment with the city you're watching from right now. We read everyone. Before we go further, the sources. This script is grounded in peer-reviewed research. Specifically, a 2017 study published in the Journal of Archaeological Science by Dr. Sharon Hull at the University of Manitoba. The study that used copper and hydrogen isotope ratios to map the largest documented ancient turquoise trade network in North American history, tracing material across hundreds of miles between mine and city. And a 2021 study by the US Geological Survey, published in Scientific Reports, measuring uranium concentrations in Grand Canyon groundwater linked directly to ancient and modern breccia pipe mining. Not popular science summaries, the actual data. Now back to the story. You are standing at Chaco Canyon in northwestern New Mexico. The year is approximately 900 CE. Pueblo Bonito, one of the largest pre-Columbian structures ever built in North America, contains over 600 rooms. The economy powering it is built on rocks, specifically turquoise. Over 200,000 individual pieces of turquoise have been recovered from sites across Chaco Canyon. 200,000. And the nearest known turquoise deposit is more than 124 miles away in the Cerrillos Hills mining district near present-day Santa Fe, New Mexico. Dr. Hull's isotope analysis of 74 turquoise artifacts from ancestral Puebloan sites confirmed what had been suspected but never proven. The Chaco network was drawing material from Colorado, Nevada, and southwestern California simultaneously. 4 separate geological source areas, 4 separate mining regions, all feeding into one distribution hub. The Canyon Creek mine in east central Arizona, where turquoise was quarried from a 1.2 billion-year-old metasedimentary rock formation of the Mesoproterozoic Apache group, was worked continuously through the 13th and 14th centuries CE. The waste rock tailings from just one of its 4 excavation zones covers 4,000 square meters. One zone, one mine. The full site had 4. Researchers publishing in the Journal of Archaeological Science in 2017 noted that the discovery of a previously unmapped excavation zone increased estimates of total mine output by more than 25%. The Hohokam civilization, active from roughly 200 BCE to 1450 CE across the Arizona desert, mined coal, hematite, salt, and turquoise. They built irrigation canals stretching hundreds of miles through the Sonoran Desert. They had trade routes connecting communities that should have had nothing to share. And dates from the region's sites show mineral procurement going back to approximately 1000 BCE. The state's earliest known mines, documented by archivist William Ascarza in publications sourced from the Arizona Bureau of Mines, date to the late centuries of the Aboriginal period, between 1000 CE and the arrival of the Spanish in the mid-1500s. Now, here is the mechanism nobody explains. Mining does not just remove ore. It reshapes a landscape in 3 sequential compounding ways. First, extraction. You remove the rock with value. The hole changes how water drains. Surface water that used to feed roots now flows into the pit, Vegetation in the immediate zone weakens and dies. Second, tailings. Every mine produces waste, rock that surrounds the ore but has no market value. Ancient miners moved this material by hand and piled it near the excavation. At ancient copper mines near Lake Titicaca in Peru, documented by archaeologist Roseanne Chambers, quarry pits exceeded 20 feet in depth and 32 feet across. The waste rock piles are still sitting there. They have been sitting there for 2,000 years. Nothing grows on them. The mineral composition of the tailings prevents vegetation from establishing root systems. Third, this is the one that changes landscapes at the regional scale, smelting. To convert ore into metal, you burn it. Copper smelting requires temperatures between 1,000 and 1,100 degrees Celsius. In antiquity, the only way to hit that temperature was charcoal, and charcoal requires trees, not a few trees. Estimates from ancient smelting operations suggest 15 to 30 kilograms of charcoal consumed per kilogram of copper produced, which means several kilograms of wood per kilogram of charcoal. A single operational smelting site, running continuously for a season, can strip the vegetation from the surrounding landscape within a radius of several miles. Professor Erez Ben Yosef at Tel Aviv University has spent years excavating the Timna Valley in the Negev Desert of southern Israel. The Timna copper mines date to approximately 4000 BCE, the Chalcolithic period, making this one of the earliest known copper extraction sites in the world. The Egyptian New Kingdom pharaohs expanded operations dramatically. The cartouches of Rameses III, 12th century BCE, are still carved into the rock temple walls at the site. Inside the slag heaps, the waste layers from the smelting process, Ben Yosef's team found charred acacia wood in quantities that show systematic clearance of the surrounding vegetation to power the furnaces. The Timna Valley is desert today. It was not always desert. The trees that fed the ancient furnaces are gone, and what took their place was bare rock and wind. The same pattern is documented in Jordan. At Wadi Fainan, where Bronze Age copper mining operated from approximately 2000 BCE, pollen records extracted from lake sediments document the removal of the local forest over centuries of continuous smelting. Trees in, copper out, bare rock left behind. That area is desert today. A 2017 study published in Scientific Reports, authors including Loic Boscher and Thilo Rehren of the UCL Institute for Archaeometallurgy used ice core records from Andean glaciers to identify the oldest extensive copper metallurgy signal in South America. The pollution chemistry in the ice began 2,700 years ago. Ancient smelting fires in the Andes left a detectable trace in glaciers hundreds of miles away. That is the volume of material being burned to extract copper from the mountain range that sits above the driest desert on Earth. If deeply sourced history from primary records is what keeps you here, subscribe. It is the best way to support this work. Comment your city too. Now, the part about the copper that vanished. Between 3000 and 1200 BCE, the same centuries that saw the Egyptian New Kingdom, the rise and fall of Mycenae, the construction of Stonehenge, there were approximately 5,000 copper mine pits dug along the south shore of Lake Superior in Michigan, 5,000 individual excavation sites. The old copper complex of the Great Lakes is the best documented prehistoric mining operation in North America. The National Park Service archaeological record at Isle Royale in Michigan, where indigenous miners worked Minong Ridge for over 4,500 years, beginning around 2,500 BCE, identifies over 1,000 individual mine pits on that single island. The pits are now filled with soil and covered by forest. You walk through the trees at Minong Ridge and you're walking across the buried roofs of ancient mines. Hammerstones are still there. Fire-cracked rock from the heat and water extraction technique is still there. The ancient pit openings, collapsed and overgrown, are still there. Estimates of total copper extracted from the Lake Superior Basin during this period reach as high as 1.5 billion pounds. Archaeologist Susan Martin at Northern Michigan University has noted in published work that these figures are contested. No comprehensive study of all prehistoric mines has been completed, and the real total is unknown. But the extraction itself is not in doubt. Every significant modern copper mine sunk into the Keweenaw Peninsula was dug directly into an ancient pit. The prehistoric miners had already found every deposit worth finding along 120 miles of Michigan lakeshore. The copper is gone, but only a tiny fraction of what was extracted appears in the North American archaeological record. The question of where it went is documented, unresolved, and sitting in peer-reviewed papers without a consensus answer. The pits are real. The hammerstones are real. The missing copper is real. Before the Atacama, go east, way east, the Sahara. In 1353 CE, the Moroccan explorer Ibn Battuta passed through a southern Saharan town called Takata, in what is now the Agadez region of Niger. He found copper being smelted in local homes by enslaved workers, cast into standardized bars, and used as currency. Medieval account, ancient operation. French archaeologist Danilo Grebinar excavated the same region between 1977 and 1981 and found radiocarbon dates for copper metallurgy in the Agadez area going back to the beginning of the 3rd millennium BCE, 5,000 years ago. Copper smelting at scale, 5,000 years ago, in the middle of what is now desert. In western Mauritania, at a site called Guelb Mograine near Akjuit, French archaeologist Nicole Lambert began excavating in 1968 and found an ancient mining gallery, not a natural cave, but a human-dug tunnel, following a vein of malachite copper ore through solid rock. 4 other exploitation sites were found nearby. Radiocarbon dating placed the mining activity between 800 and 200 BCE. Furnace remains and slag confirmed the ore was smelted locally in the Sahara, in a place that today sees almost no rainfall and supports almost no vegetation. The Sahara was not always the Sahara. The African humid period, the Green Sahara, lasted from roughly 11,000 to 5,000 years ago. Grasslands, lakes, hippos, forests. The drying was driven by orbital shifts, but the timeline of Saharan drying overlaps precisely with the timeline of Saharan mining. The charcoal in the ancient furnaces came from somewhere. It came from the trees. In a landscape already under climate stress, systematic deforestation to feed smelting operations is not a trivial additional pressure. The iron mines of ancient Meroe in what is now Sudan operated from the 7th century BCE to the 6th century CE. Over 1,000 years of continuous iron production. A study published in the Journal of African Archaeology documented for the first time direct evidence of ancient iron mining in the Meroe region, with ore extracted from exposed Nubian sandstone surfaces across the surrounding plateau. 1,000 years of burning charcoal in the Nile corridor. The desert there today is called the Nubian Desert. Now go south, 1,700 miles south, the Atacama Desert of northern Chile, the driest non-polar desert on Earth. Some weather stations there have never recorded measurable rainfall. NASA used it for Mars rover testing. And in the middle of this desert is one of the largest holes humanity has ever dug. Chuquicamata, 4.3 kilometers long, 3 kilometers wide, 1 kilometer deep. The Chuquicamata mine produces 650,000 metric tons of copper annually. In a January 2024 satellite image acquired by Landsat 9, published by NASA Earth Observatory, the waste rock piles around the mine appear as massive gray formations flanking the pit. Tailings ponds, holding residual material from the ore enrichment process, cover additional square kilometers of desert floor. The mine benches appear from orbit as concentric rings cut into the earth. The modern mine is visible from space. The ancient mine is also there. A 2021 study published in Minerals Journal by researchers at Universidad Católica del Norte documented the copper mining economy of the Atacama from approximately 1500 BCE through the Inca horizon ending around 1540 CE. The Incas took control of Atacama mining districts in the mid-15th century. When the Spanish arrived, they found active mines, functioning infrastructure, and a workforce already organized around extraction. 3,000 years of prior operation. That 3,000-year operation left waste rock. It left stripped hillsides where the smelting fuel came from. It left mineral-contaminated soil. The Atacama sits in a rain shadow from the Andes, which is real and geological, but the Atacama also sits on top of thousands of years of stripped vegetation, depleted groundwater, and accumulated mining refuse. No single cause made it what it is, but you cannot tell the full story of the world's driest desert without counting what was taken out of it and what was burned to take it out. Back to the Grand Canyon, the uranium. The breccia pipes of the Colorado Plateau are chimney-shaped geological formations unique to the Grand Canyon region, and 1 or 2 locations in China. They are collapse features in ancient limestone filled with rubble, concentrating uranium ore at extraordinarily high grades. The U.S. Geological Survey. 2021 study published in Scientific Reports by a team including David Bexfield confirmed there are thousands of these formations beneath the Colorado Plateau, but only a relative few contain miniable uranium. The Orphan Mine, south rim of the Grand Canyon, 2 miles west of Grand Canyon Village. Daniel Logan Hogan staked a copper claim there in 1891. He worked it on and off for decades and shipped no ore. He sold it in 1946. The new owners found uranium in 1951. Between 1956 and 1969, corporate successors extracted 495,107 tons of ore. The yield, 4,257,571 pounds of uranium oxide. $40 million worth from a single breccia pipe on the rim of a national park. In 2012, the federal government withdrew over 4,000 square kilometers of federal land around the Grand Canyon from new uranium mining applications for 20 years. The withdrawal was challenged by mining interests and upheld by the 10th Circuit Court of Appeals in 2022. As of 2020, 2 uranium mines in the region remain in standby status. Horn Creek, inside the national park, has groundwater uranium concentrations reaching 293 micrograms per liter, the highest measured in the region, directly adjacent to the old orphan mine workings. This is not speculation. It is in the USGS study published in Scientific Reports in November 2021. The great unconformity runs through the canyon walls like a line drawn in pencil. 520 million year old Tapeats sandstone sitting directly against 1.7 billion year old Vishnu schist. In between, more than 1 billion years of rock that are simply gone. First identified by geologist John Wesley Powell in 1869 during his first Colorado River expedition. A 2022 study in the journal Geology, led by University of Colorado Boulder geologist Bara Peak, found that the gap in the rock record reaches 1.2 billion years at its largest point in the Western Canyon. The rocks were removed. What removed them, supercontinent breakup, ancient glaciation, tectonic erosion, is still actively debated in the scientific literature. There is currently no widely accepted single explanation. But here is what there is evidence of. 9,000 years of continuous human presence, 4,300 documented sites of prehistoric activity inside the park, turquoise and copper extracted and traded across a network spanning hundreds of miles, uranium-rich breccia pipes of a type found nowhere else on Earth except 1 or 2 locations in China, groundwater contamination at the highest levels measured in the region, and a landscape that, from the South Rim, looks like nothing has ever lived there. In 1850, Samuel O. Knapp, the agent of the Minnesota Mining Company, was digging in Michigan when his crew hit something at 26 feet below the surface. A copper mass 10 feet long, 3 feet wide, weighing over 6 tons. Sitting on a wooden crib frame of oak billets, the wood so compressed and darkened it had lost all structural integrity. A knife blade would go into it as easily as into peat bog. The ancient miners had raised it 5 feet off the bedrock and then stopped. Too heavy to move, they had left it there and walked away. Around that mass, in every direction across the Keweenaw Peninsula, were more pits, thousands of them, each one with a pile of waste rock beside it, each one emptied of whatever metal it held. The surrounding forest eventually reclaimed the waste piles, slowly, over centuries. The roots found a way through the mineral debris. The canopy closed back in. But the story does not end on Minong Ridge. That same summer of 1850, while Knapp's crew was puzzling over a 6-ton copper mass abandoned on an oak scaffold by unknown hands, surveyors in the Negev were documenting ancient slag heaps at Timna that stretched for miles. The Egyptian miners who worked that copper site under Rameses III in 1200 BCE were gone. The temple carvings with royal cartouches were still on the walls. The acacia forests that powered the furnaces were not. The land that once supported enough vegetation to fuel continuous high-temperature smelting had been stripped and not grown back, and would not grow back. 3,000 years later, it was still bare, still scraped, still looking the way a place looks after everything of use, has been taken out of it, and nothing has been put back. Deserts are not all the same. The Sahara dried because Earth's orbital cycle shifted. The Atacama dried because the Andes grew and cut off the rain. The Negev is dry because that is the climate of that region. These are geological and atmospheric realities. But sitting inside every one of those deserts, under the bare rock and the mineral dust, is the documented evidence of thousands of years of extraction. Mines, waste piles, slag heaps, stripped hillsides, poisoned soil. The archaeological record of people who found something in the ground, pulled it out, burned everything around it to process it, and left. The forest grew back at Isle Royale. Slowly, but at Timna, where the ancient furnaces burned through the last of the acacia trees 3,000 years ago, the forest did not come back. The wind came instead.